familiar with. So now we're going to talk about convolutional neural networks just as an analogy to graph neural networks. So if you compare graph neural networks to convolutional neural networks, they're for computer vision. That means their input is usually a picture. And the output of the neural network, it depends what you train it for. So your output could be predicting the main object in the picture, so classification. The output could be maybe a textual description of what's in the picture, or the output could be maybe some segmentation. So in the same sense, graph neural networks are also neural networks, but instead of the input being a picture, the input now is a graph. Graph consists of nodes and edges. We're going to explain those in just a little bit also briefly. And what is the output of graph neural network? Give it a whole graph. At the input, what is the output? Well, it depends how you train it. So the output could be classifications, so node classification. So for every node, maybe you want to output some class. Here, maybe node number 0 likes basketball. So maybe that's what you're interested to predict. The output could be link prediction. So here, you can give it 2 nodes, and it tells you these 2 nodes have this edge property, or maybe they should be connected via an edge. Or the output of the graph network could be graph classification. So you can, for example, you can convert an entire computer program into a graph, and you can put this graph of the computer program into a graph neural network, and the graph neural network could tell you, will there be a virus, or is there a virus in this program? Of course, if you train it for such a task, it could maybe solve this task. So before we dig into the details of the graph neural networks, we're going to briefly explain what is a graph. I'm sure most of you here have heard of what a graph is, but just in case, this is a good refresher. So a graph consists of nodes and edges. Nodes are usually drawn as circles, and edges as straight lines that connect the nodes. So for example, you can think about a social network, an online social network. You can put this online social network in the shape of a graph. Here, every node could be a user, or every node could be maybe a comment or a post on the social network. And an edge could mean an interaction. Maybe if 2 people are friends, you have an edge between them, or maybe if someone liked the post, there's an edge between them, etc. And nodes here could have features. So if you're thinking about a person node, the person node could have some age range, could have a gender, have a location where they live, and maybe could have the language that they speak. At a comment node, I wonder if I could do like a laser. A comment node could have the language representation as its feature. Maybe it's like the word2vec or some kind of language model. And if you want to do machine learning on this graph, what does it mean? Well, you could do multiple things. You could do node classification, as we said. So graph neural networks can do node classification. This means you are mapping your input graph to some kind of output graph. Here in the output graph and the input graph, every node present in the input is also present at the output. And we're basically trying to map every node from the input space into maybe the advertisement that this user will like. So perhaps this bottom right user likes fashion, some middle user likes artwork, some user likes car, and you are given some of those labels, perhaps using some kind of by processing your log files, and you are interested in predicting the label for some node that you don't know their advertisement interests. So you can do that by graph neural networks. And the way this is usually done, you can train a graph neural network on this kind of task. There are many graph convolutional or graph neural network models. For example, the GCN model of KIP, there's so many models, including this Mixhawk paper over here. So basically, each node will learn how to aggregate features from its neighbors. And most models will basically get average of their immediate neighbors. And some models will take the average of further neighbors. That's at every layer. So if you stack up more layers of this graph neural network, then you're basically getting information from further and further neighbors to do this prediction. And graph neural networks can also do link prediction. So on the same kind of graph, maybe you're interested to predict whether 2 nodes should have been friends, or if you should suggest one to be friend with the other. Also, you can do graph classification using graph neural networks. So here, your input could be an entire graph, and your graph neural network could be trained to output some graph level prediction. So for example, chemical molecules could be described as a graph. And if you put a chemical molecule, maybe you want the model to give you the output. For example, how much energy do you need to break up the molecule into its constituent atoms? Because graphs are general data structures. So we just showed how you can put social networks out of the graph, but you can put lots of data into a graph. If you convert your data into a graph format, then you can immediately run graph neural networks on top of that. So because graphs are general, that means the tasks that are solved by graph neural network can also be generalized to different tasks. So we're going to give a few examples of some graphs. And if you apply link prediction or node classification on those domains, what does it mean? What kind of utility do you get? So if your graph is a social network, as we just saw, your nodes here could be, let's say, users, comments, etc. Your edges could be friendships, like, etc. And if you do node classification on this graph, maybe you can get a utility of ad preferences. You can predict which advertisements each user likes. And if you do link prediction, you can maybe do friend suggestion. What could you show on the home feed? If your graph consists of drugs, so drug-drug interaction. So here you could have ibuprofen in one node, Tylenol in another node, maybe alcohol in another node. And here the edge could mean interaction. That means someone who takes drug 1 shouldn't take drug 2 at the same time, otherwise there could be problems. So here, if you do node classification on this kind of graph, you could be predicting the biochemical or biophysical properties, for example, the boiling point or the toxicity of the drug. And link prediction means predict interactions. So maybe someone doesn't know that they shouldn't take drug 1 and drug 2 at the same time. Link prediction can say that, yes, you shouldn't take them. Of course, such a prediction should always be tested, perhaps in a lab or something. Your graph could be, for example, user video watch graph. Here, this is the bipartite graph. You have users on one side, you have videos on the other side, and an edge means maybe the user watched the video or liked the video. If you do node classification, then you could classify what the videos are about. And if you do link prediction, you could be doing video recommendation. And if your graph was a citation network, each node could be an article. Each edge means a citation. So if a paper cites a paper, then in your graph, there's an edge from the citing paper to the cited paper. If you do node classification, then you could be interested in predicting the article category. What is this article about? Is it a science article, sports article, etc.? And if you're doing link prediction, maybe you're trying to predict related work. So are these two papers similar or related in some way? And of course, there are many, many more applications that we have time to discuss. So here we just present some of them. So graph neural networks have been used to estimate finding the shortest path, measuring distances between two graphs, subset selection, even solving integer linear programs, and many more problems. So maybe I'll just take like a minute break if anybody has any questions. If not, I'll just continue right now. Does anyone have any questions? Thank you. Okay, so now we're going to talk about high level of TF-GNN, what we're trying to demonstrate today. So we're going to do some high level overview of TF-GNN right now, and then we're going to show some practical considerations. Maybe people are, when they want to train GNNs, they have things they want to think about, and how does TF-GNN solve these practical considerations? So roughly speaking, you would usually have some kind of training pipeline. Inside this training pipeline, you have some graph data, could be a social network, drug-drug interaction graph, etc. And you want to train some GNN model. So for example, the graph data could have nodes, edges, and their features. The labels could be at the node level, at the graph level, or at the edge level. And your GNN model, for example, could be GCN, using some kind of distance encoding for link prediction. So these are valid options. So let's look at these three pieces: the training pipeline, the graph data, and the GNN model. And for each of them, any of you could have some considerations, and let's see how you can solve them with TF-GNN. So the first consideration we're going to talk about is the graph data. So the question is, what is your data store? So your graph could be stored in many different formats. For example, your graph could be stored on some relational database like CSV files, SQL, Spanner, any relational data store. Or your graph could be serialized. For example, it could be stored in TensorFlow record files. TF-GNN provides something called a unigraph, which can read serialized data and relational data. And maybe your graph is some academic graphs, for example, an OGB graph, Network X, etc. Also, TF-GNN has some readers for a bunch of those academic setups. And it's very easy to make a new data source so that you can be able to load it into TF-GNN. Now, the next consideration you might be thinking about is your GNN model. So it depends, of course, it depends on the data that what is the nature of your graph. The GNN model will depend on that. So your nodes could be images, your nodes could be videos, your nodes could be textual documents. And because TF-GNN is written in TensorFlow, that means you can use any TensorFlow model for maybe image processing, video processing, or text processing on the nodes. And the models could be trained or untrained. You can freeze them, you can fine-tune them. You have that choice. And your task could be node classification, edge classification, graph classification, etc. In TF-GNN, we implement many standard objectives for node, graph, edge, supervised, unsupervised, semi-supervised learning. So you can just plug and play all those pieces. And what if you know something special about your data? You have some kind of inductive bias. You could use any TensorFlow layer, for example, residual, maybe equivariant, Euclidean equivariant layers, etc. The final consideration we're going to talk about is the training pipeline. So your pipeline might be standard, as in you have a data set, you put the data set through a model, you try to optimize an objective function. We have something called a TF-GNN runner, which basically you have to write just a configuration file. You don't have to write any real code, just a configuration file to wire your pipeline. And this works for the standard use case. However, you might have some custom use case. Maybe you want to adjust the gradient somehow. Maybe you want to, your graph itself is latent. Maybe you want to do some kind of transfer learning. Oops. So we have an examples directory that shows 20 to 50 lines of code for training. So you can start there and you can implement your custom training loop over there. And the next consideration on the graph size. So maybe your graphs are small. We have ways that you can do full graph training. So you can see the whole graph at every training step. Maybe your graph is medium sized, less than 100 million edges. You could do in-memory on-the-fly sampling. We're going to demo these two in the first tutorial, how you can do this. And maybe your graph is very large. So you have billions of nodes and edges. So we have a distributed sampler so that you can train very, very large graphs. So that was it for the background portion of graphs, GNNs. And now we're going to dig into the practical portion of this section. So we're going to show how you can train TF-GNN models on a single machine. Does anyone have questions in the meanwhile?